Welcome everybody to the Geological Society in Burlington House here in London. My name's Owen Green, I'm from the University of Oxford, and I'm going to talk to you about the William Smith map. And what better place to start than with a portrait of the man himself. This portrait was presented to the Society in 1880, and it really conjures up an image of a man who was born and brought up in Oxfordshire and then worked in Somerset for a large part of his life. Now let's just have a look at the geological map. Well, here we have the geological map that Smith produced. It was actually originally published in 1815, but it took him 15 years to actually produce and work on and getting the data for this map. So when we look at it, we can actually see two components to it really. One, as a geologist, you look at this map and you see geological data. But in its own right, it's actually a beautiful map. It was hand painted, and we're going to see some very nice close-ups of some of the individual sheets. So Smith spent a number of years actually trailing around the country to get data to put on his map. And then with the help of John Carey, he actually managed to get a base map that he could actually hang his geology on. Well, prior to Smith actually producing his large map of England and Wales, he also collected data from around the country. And one of the principal areas that he'd worked in was down in Somerset when he was employed as a canal engineer. And the Somerset map is very, very interesting and well worth looking at in a little bit more detail. Here's the original map in front of me. It was actually based on a tourist map. We'll have a quick look in detail at this Bath map, and you will see on the copy that we've got here that there are some of the strata has been hand coloured, and it reflects the topography of the area. Smith was learning that in actually preparing a map, you needed to understand the topography in order to lay the geology on top of that. Two men of the cloth, the Reverends Townsend and Richardson, accompanied William Smith on a journey around the area of Bath, looking at the outcrops. They were just amazed at how Smith could predict what was going to be on the other side of the valley. And from this, Smith was beginning to develop one of his first principles, that is the law of superposition of strata, in that older strata will always underlie the newer strata. Smith managed to demonstrate and show this on his map by colouring strata of different ages. And it's this whole colouring that has actually persisted even into geological maps of the 21st century, and it is a key part of geological mapping. And we can see that in detail on this close-up of Smith's sheet in the Bath area. The detail on here is quite considerable because he obviously spent a lot of time working in this area, and so a lot of the small outcrops are actually included. But one of the things you can see is this huge swathe of green material over on the eastern side of the map. So to a geologist, a lot of the green strata indicated there will be Cretaceous, the chalk strata. So Smith was beginning to realise that it was possible to follow the strata across the country. So here we've got a map of southern England. There's London situated here in the centre, Kent down to the south. And this is a map that illustrates the Mesozoic strata that is represented by the anticlinal structure in the Weald. And Smith managed to actually draw a cross-section through this, essentially north-south on here, and here we have a close-up of that section, and we can see that he's marked on here that the strata is dipping both to the north and to the south. This is the first geological section that actually demonstrated this sort of structure and just showed how important it was that maps and sections go hand in hand when you're doing a geological interpretation of an area. And again, this is something which is used by all students today to understand the geological structure and the geological history of any area that they're mapping. So Smith really was a trendsetter when he was beginning to do this work. Now my colleague here, Mike Searle, is now going to talk us through the section that Smith did in the south of England. Thanks, Mike.
Okay, well, as Owen has pointed out, the geological mapping that Smith did was absolutely groundbreaking in the fact that it was the first major geological map of England and Wales. And fundamentally, he was the person who really initiated the whole art of geological mapping. And that involves not only putting colours on the map, following the rocks in two-dimensional space along the map, combined with a stratigraphic key, which is absolutely crucial, so you know which strata you're looking at in the individual parts of the map. And thirdly, the most important part is the structural concept. So we have the two-dimensional map, a 2D cross-section through the map, and a stratigraphy. And that forms the basis of all of the geological mapping that has been done ever since 1800 in the UK and worldwide. And these are two beautiful cross-sections. This one here is a cross-section from London to Snowdon, which is the highest mountain in Wales, and it shows the general stratigraphy going from the oldest Paleozoic rocks in North Wales, and these funny-looking granites, which are actually probably the andesites of Llanberis, all the way to the London Basin over here. This geological map is one across the Wealden area, and it shows the Wealden anticline, which is the first structural cross-section ever produced in the world. This, of course, led on to the concept of restoring and balancing cross-sections, making sure the stratigraphy over here is the same as the stratigraphy over here, and using the structures to actually unwind what was happening as you wind back time. So following the William Smith map of 1815, it soon became apparent to most people who were interested in the natural world that we need to get this country mapped. So the Geological Survey of Britain was started around the tail end of the 1830s, and following that, every part of the country was being mapped in detail. Now in those days, stratigraphy ruled the roost, and the director of the Geological Survey at the time, Sir Roderick Impey Murchison, who was a very powerful country gentleman, he was working on the Silurian rocks of Wales. And when they came to interpret the rocks of Scotland, he thought that all of the metamorphic rocks that form most of the central and eastern part of Scotland were Silurian because they stratigraphically appeared to overlay the Cambrian and the Ordovician. And this was the going model of the day when everyone agreed with Sir Roderick that the Silurian of eastern Scotland overlay the Cambro-Ordovician, which overlay the Precambrian. And it was only in about the 1860s when Nicol from the University of Edinburgh and Callaway and Lapworth, who was professor in Birmingham University, all of them were working up in northwest Scotland, that they discovered thrusting. And Lapworth was the first person to actually identify a thrust fault. In other words, a fault that puts older, deeper rocks over younger, shallower rocks. And anyone who's been up to the northwest of Scotland, now we think of the Moyne Thrust as being the classic thrust belt of the world where this was apparent. And above the Moyne Thrust are all these metamorphic rocks, which are highly ductilely deformed and much older in time. So Callaway had this, and Nicol had this big argument with Murchison and Geekie of the survey, whether this was stratigraphic or structural. And when Murchison died, he was a very powerful character and everyone had to follow his model. Geeky took over running of the survey, and he decided to send a team up to map in great detail the entire Northwest Highlands of Scotland. And this was in the 1880s when Peach, Horne, and 5 or 6 other geologists spent 20 years mapping in great detail all of the Highlands of Scotland. And their maps, these maps here, date from that period, 1888, and they are the most spectacular and beautiful maps created. And you'll see that they have the complexity of modern day maps. So not much has changed since the 1880s in terms of geological mapping of parts of Scotland. What has changed is the interpretation of the structure, and particularly the Moyne thrust. And this was the first place in the world where thrusting was first discovered. And Lapworth was the man who discovered thrusts. So when the Northwest Highland Memoir was published, which was a result of 25 years of mapping in 1907, this is the Memoir of the Northwest Highlands of Scotland by Peach, Horne, Gunn, Clark, Hinksman. This really overturned the entire stratigraphic story of Murchison. It was very clear that the Moyne schists over here overlay with a structural context in a thrust fault the foreland of Laurentia over here, which comprised the old Precambrian rocks of the Lewisian, overlain unconformably by the Proterozoic conglomerates and shales and sandstones of the Torridonian section, overlain by the Cambrian and the Ordovician marine limestones that we see all the way from Durness on the north coast of Scotland down to the Isle of Skye. And the real area of complexity is this region here. This is the Assynt window, where the Moyne thrust, this line here, has been folded up and domed around the deep structures exposed in the middle of the Moyne thrust. And it's only through this late doming that we see the geology underneath. And this map here, the Assynt sheet, produced by Peach and Horne and their colleagues in 1888, is one of the most beautiful examples of this type of mapping. So the discovery of thrusts was really important worldwide, and they had a international geological field trip up to the Northwest Highlands in 1907, when people like Arnold Heim came from Switzerland and exported the theory of thrusting and fold naps to places like the Alps and even the Himalayas. So really the Assynt window is one of the most important geological maps produced anywhere in the world at the time. And this led on in the 1980s to the next major revolution in how to interpret structural geology from geological mapping. And that was the concept of balancing and restoring cross sections. So Dave Elliott and Mike Johnson from the University of Edinburgh and Dave Elliott from Maryland, used the Peach and Horne maps of the Assynt window to create these geological cross sections. And they used the stratigraphic concepts developed as a result of William Smith to interpret and balance the cross sections. In other words, they were getting the stratigraphic thicknesses correct all the way through the sequence. Then they went a stage further and they interpreted the minimum amounts of crustal shortening by reconstructing the balanced cross-section that you can map and see today to the restored cross-section. And the difference in length between the restored cross-section, the present-day cross-section, gives you the minimum amounts of crustal shortening. From then on, from 1980 onwards, balancing and restoring cross-sections was taken worldwide. And this is an example here of a geological cross-section across the Alps. This is from a paper by Stefan Schmidt et al. Everything in colour is the geology that is interpreted by mapping at the surface. And of course, the surface mapping of the Alps never goes down to 30, 40 kilometres depth. So you have to use geophysics to interpret what's going on in the deep crust. And this section here is a geological cross-section across the Alps, showing the geological structure combined with the seismic structure of the deep crust. And this is how mountain belts are interpreted today, using a combination of everything that stemmed originally from William Smith. So another fascinating story about geological mapping occurred in India, and this was during the time of the East India Company and the British Raj, when it became apparent that what we needed to do was to map out all the frontier regions of the Indian Empire, as it was called in those days. And this included most of the high peaks along the Karakoram, the Himalayas and South Tibet. So this was a fantastic scientific expedition that started in 1802 with the initiation of the Great Trigonometrical Survey of India. And that's when triangulation was all the mode for creating the first topographic map of the countryside. And this was done using theodolites in those days. And the first director of the Great Trigonometrical Survey was William Lambton, who started in 1802 with the baseline, a very accurately measured baseline in Madras on the east coast of India. And at the time they were using theodolites, which are enormous great machines like this, which were literally dragged by camel, by elephant, by porters, by river, raft, anything, along the length and breadth of India. And you can see from this map here, this is William Lambton, who was the first director of the Great Trigonometrical Survey, and he was succeeded by George Everest, not called Everest, Everest, who succeeded him. And this map here shows the extent of the Great Trigonometrical Survey of India. And this went on for about 30 years when they were measuring baselines, triangulating all the way up from Madras along the length and the breadth of India. And the most important regions were up here in the north, which is the great frontier of the Himalayas, and that divided the British Empire to the south from the Russian Tsarist Empire to the north. And at those times, this was during the Great Game, when all these pundits were sent out in disguise across Tibet to figure out which rivers drained into which rivers in India from Tibet. And the frontiers were being actively drawn up. So the pundits and the Great Game is a fantastic story, and it went on all the way up to about the mid 1900s, when the first topographic maps were made across the country. Now these topographic maps were, again, beautifully illustrated, and this is one topographic map of the Mount Everest region here. And this was originally done in 1921, when the first detailed geological maps were made of distinct parts of the Himalayas. Following the topographic mapping, it became very clear that what was needed next was geological mapping. And the first geological map of the Himalayas, which is an enormous mountain range, it's 2,500 kilometers long. The first geological map was produced by Burrard and Hayden in 1907 in this spectacular memoir, Geology and Geography, the Himalaya Mountains and Tibet. And this is the map that accompanied that memoir. And you can see that most of it was concentrated in regions around Lhasa and Tibet and regions around the Kashmir region in the west. And a lot of the rest of the Himalayan range was a blank on the map. So these blanks on the map were increasingly used all the way across for the excuse for these mountaineers to go out. People like Eric Shipton, Bill Tillman, who were some of the most famous explorers who traveled the length and the breadth of all these parts of the Himalaya and the Karakoram, right up to the World War II. So having mapped out the topography in as much detail as possible in the 1910-1920s, the next job was to put the geology on that. And some of the early geologists who accompanied the 1920s expeditions to Everest from the UK included a geologist. This was A.M. Heron, and this was his geological map of the Mount Everest South Tibet region from 1921. So the next great step forward was a two-man expedition from Switzerland that comprised Arnold Heim, the guy who went to northwest Scotland with the Peach and Horn expedition to figure out how thrusts and folds and gnats work. Arnold Heim brought with him a young geologist called Auguste Ganser. Ganser wrote this spectacular book, The Geology of the Himalayas, in 1964, having spent 2 or 3 expeditions in the central part of the Himalayas And the rest is a sort of compilation from some of the early geological mappers who were mostly English commissionaires who were stationed up in the hills. And this was the Ganser map in the back of his book from 1964, which is really used as a sort of Bible of the first real compilation, a review of everything that was known about the Himalayas in those days. And in those days it was mostly stratigraphy, very little structure, but Hyman Ganser did some extraordinary work, and this was at a time when they were only given permission to go up to the border regions. Augusto Ganser actually went in disguise, crossed over the mountains illegally into Tibet, in disguise, spent some time in Tibet, and during that time he discovered the suture zone. He discovered all the aphylites of the Amlangla Kyogar region, which is up here in southern Tibet, and this is what we now know as the collision zone between India and Asia. The suture zone that runs all the way from the northwest frontier of Pakistan, all the way down southern Tibet to the Namche Bawa region, eastern syntaxis, and thence down into the Indo-Burman ranges to the south. So Ganser was the first person to really discover the aphylites in the suture zone. Hyman Ganser discovered the main central thrust, which is this major crustal scale thrust, very similar to the Moyne thrust, and they also discovered above the thrust was the inverted metamorphic sequence of the Himalayas. Very, very important rocks. These were the first descriptions of hotter, deeper rocks overlying younger, shallower rocks, all in metamorphic grade. And they were absolutely correct. As you hike up any of these valleys in the Himalayas, all of the metamorphic isograds are actually inverted. They're upside down. So the hotter rocks are thrust over the colder rocks. And a lot of work has been done since then on how to take this forward in terms of thermobarometry, figuring out the pressures, the temperatures, and the depths that those rocks formed at, and most important, the geochronology. So mostly using uranium-lead isotopes on minerals such as zircon, alunite, monazite, rutile, things like that. And that gives you the timing of peak high temperature metamorphism, and timing of granite melting. And then it became apparent with all the geochronology that was done along the Himalayas that instead of being Precambrian, a lot of this metamorphism was very young. It was Cenozoic. And the granites that form many of the highest peaks of the Himalayas, including peaks like Makalu, Shishapangma, Lhotse, Makalu, basal parts of Everest, these were all formed around 20 million years ago, which is incredibly young. So the Himalayas then became the stomping ground to figure out how orogenic belts work in time and space. And this was done by a combination of all of the methods that we've seen already: geological mapping, stratigraphy, structural geology, pressure temperature thermobarometry, and geochronology. So the toolbox of the geologist is now expanding greatly since the old William Smith days. So after Ganser, a lot of people went off mapping all different parts of the Himalayas, and in the 1990s and 2000s, there were groups from Europe, North America, going all over the Himalayas doing exceptionally detailed mapping. And this was, of course, combined with some of the oil exploration work that was being done in the foothill ranges, particularly down here in the south, the Potwal Plateau, and the basins around the main boundary thrust down here, all of which are oil-bearing and are very well constrained through seismic data and well data. And this map here was compiled in 1991 by myself and Asif Khan from Peshawar University. And what we did was take in all the oil company data from the south, combined with seismic sections to get the deep structures of the thrust belt. Once you're over the main boundary thrust of the Himalayas, all of this is metamorphic rocks going up through the Kohistan arc, this incredible island arc sequence that's caught up. This is a Japan Mariana island arc type scale, caught up between the Asian plate and India. The main mantle thrust being the remnants of the suture zone between the Indian plate and Asia. And to the north of Indian plate, Kohistan arc, is the Karakoram range. The Karakoram is the highest topographic mountain range on the planet. Most of the 8,000 metre peaks and over 7,000 metre peaks are concentrated in this belt along here, from the Hindu Kush along the High Karakoram range all the way down here. So that's just one example of maps that we're using to this day, using the same techniques. And zooming in a bit more, well, I should actually say that the other great advantage that we had mapping in the Himalayas and the Karakoram was the satellite photography. So this is an example of a Landsat photograph of the central Karakoram regions here. This is the central part of the Karakoram. The Karakoram fault, which is a big active strike-slip fault, runs, you can see it affecting topography all the way down here. This is the Siachen Glacier, and it runs right down here through the Nubra Valley and all the way down to southwest Tibet. Unfortunately, this region here has its political problems because it's right on the boundary of Pakistan, India, and China. The triple junction is actually at the Siachen Glacier, where they've had the world's highest battle going on for about 20 years. So a lot of the early geological mapping of the Karakoram and parts of the Himalayas was linked in to mountaineering expeditions. It's the only way you could get up there and have a base camp for 3 months at K2 and explore and map all this region around here. So that's what we did in the 1900s and early 2000s, and this is the result of a geological map using all of the techniques that I've been talking about, using the William Smith techniques of stratigraphy, mapping, structural techniques to provide balance and restored cross sections, metamorphic techniques, particularly thermobarometry, figuring out the pressures and temperatures of peak metamorphism and therefore the depth at which those rocks were brought up, and geochronology, uranium-lead geochronology in particular, which gives you the timing of peak metamorphism and peak melting. And it's all of those factors that enable us to interpret how these mountain belts formed. And just one other piece of interest here, this is the Nanga Parbat Massif, another of the 8,000 metre peaks, but it's actually not in the High Karakoram or along the main part of the Himalayas. It's a kind of isolated bit right around the western syntaxis of the Himalayas. And when the famous geologist Wadia from the Himalayan Institute and people went up there in the 1940s, they thought that all these high-grade metamorphic rocks were Precambrian. And we've got samples now collected from up in the Raikop Valley up here to fairly high up Nanga Parbat, which date the peak metamorphism to less than 1 million year old. So these are rocks that were buried down to depths of about 30 to 40 kilometers in the crust in order to get those mineral assemblages of silimonite, cordierite, leucogranite, lignitite. And they're now sitting at 6,000 to 7,000 meters on Nanga Parbat. So Wadia originally thought these rocks metamorphic, they must be Precambrian, just like Blackworth did in northwest Scotland, like Murchison did in northwest Scotland. And he would have been the first to be amazed that these rocks are actually the youngest metamorphic rocks, the youngest granite anywhere in the world, and they were formed 1 million years ago. Okay, another fascinating part of the geological mapping of the Himalayas story is in the Mount Everest region of Nepal and South Tibet. And this was the region that the British concentrated on with all their mountaineering expeditions in the 1920s and 1930s. This was when George Mallory, who disappeared on Everest with Sandy Irvine later on, he went on the first of his 4 Everest expeditions in 1921, and on that expedition was a geologist, A.M. Heron, who made the first geological map of the Mount Everest region here, which is an amazing piece of work. Following that, there were geologists like Noel Edell from Cambridge, who went up there and collected fossils all the way up from the North Pole. None of these expeditions succeeded in summiting Everest. Lawrence Wager, who went on to become the professor of Oxford of Earth Sciences, or Geology and Mineralogy as it was then in the University of Oxford, he got got to the highest peak on the northern ridge of Everest, and Wager collected samples all the way down, which are used to this day to constrain the metamorphic petrology, the mineral chemistry, and the thermobarometry. So the Everest region really was a playground for figuring out structures, how the Himalayas formed. And this map here, the first version of which was compiled in 2003, and later with the addition of the Makalu region, 2007, is a result of about 5 or 6 expeditions from both the Nepal side and the Tibetan side. And the summit of Everest is right here, and these cross sections go east to west, lateral sections along the strike of the mountain, and north to south. And they show some extraordinary things. We've known since the first ascent of Everest by Hillary and Tenzing in 1953 that the summit rocks of Everest are actually Ordovician limestones. They're unmetamorphosed limestones, and they still have little tiny crinoid fossils in them. All the rocks beneath this major detachment fault, which is called the Chomolungma detachment, are metamorphic, with the Everest series being the lower grade, and all the rocks in red are the leucogranites. These are the highest grade metamorphic rocks derived from partial melting of sedimentary rocks. Down here, the green is the sillimanite gneiss, which are metamorphosed Neo-Proterozoic Hymantus series rocks. And Everest region was one of the critical areas where low-angle normal faults were first discovered. It may be surprising that the highest mountain on Everest is cut by 2 faults, which are both normal faults. Normal faults are generally associated with regions of extension, like East African Rift, Red Sea, Basin and Range Province. Himalayas, we know, has been under north-south convergence ever since 50 million years, the timing of the collision of India and Asia and the closing of the Neo-Tethyan Ocean that lay between them. So how on earth can you get normal faults operating in a compressional mountain belt? Well, this detachment here is a major structure. And along the Rongbuk Valley in southern Tibet is one of the only regions that you can actually trace this normal fault for 70 kilometers from the summit of Everest to where it disappears under the Tibetan plateau way up here. And this fault is no more than about 15 degrees dip on the summit of Everest to about 5 degrees dip. It's almost horizontal in places along the Rongbuk Valley here. And it puts unmetamorphosed rocks above very high-grade rocks. So there's quite a big jump in pressure and temperature, which means that all of these rocks, which were formed at 30 to 20 kilometers depth underneath Tibet, have been extruded south beneath this passive roof fault of the South Tibetan detachment. And this gave rise to the model of channel flow, which is now pretty well established along all parts of the Himalayas. Most of the channel flow was actually formed during the melting of the leucogranite, so it formed between 25 and 90 million years ago. And this detachment is now dead seismically, so it's not active. It was operating during the Miocene. And after this locked up and all the Himalayan granites formed, when Everest and the Himalayas reached the highest topography, thrusting propagated towards the south sequentially to the main central thrust, then to the main boundary thrust, and the one that's active today is the main Himalayan thrust, where all the earthquakes are rattling off today. So the Great Gorkha earthquake of 2015 occurred on the main Himalayan thrust, which is the active boundary in which India is under-thrusting the Himalayas and Tibet. So this project on Everest has involved everything that we've talked about from William Smith onwards. How to make a geological map, and this involves crawling all over the ground, meticulous mapping over many years, construction of cross-sections in unmetamorphosed rocks, restoring those cross-sections to figure out the amounts of crustal shortening, then using pressure and temperature data to figure out the depths those rocks formed, geochronology to figure out what time they formed, and then you have everything you need to make your model. A map, a cross-section, 3-dimensional cross-section, pressure, depth, temperature, time. And it's only when you've done all of those that you can come up with a reasonable tectonic model for how the Himalayas formed. And it all goes back to original geological mapping, which is absolutely critical. And the great William Smith started this off, and we are continuing it to this day with a lot of help from other branches of geology.